Good evening, students. So, in the last class, we were able to finish the eigenvalue problem for discrete system. There is a part of free vibration problem in which we first need to obtain the eigenvalue and eigenvector or natural frequency and the mode shape. This discrete system is an approximation because here we consider the spring is having stiffness, but the spring mass we ignore. Similarly, if some mass we are considering, we consider the mass as rigid. We don't consider the flexibility of the mass. So in actual system, you may find that a particular object will be having both mass and flexibility together. And sometimes it's difficult to distinguish whether we will consider only mass or only stiffness. Like if we have beams which are very thick, then it will be having the flexibility also, or the stiffness also, and the mass together. So such systems, the mass property and the stiffness properties are distributed throughout the system. If we consider the extension of the beam, if let us say beam is having one dimension very large as compared to the other two dimensions, the width and the height. But if we consider, let us say, width is also large enough as its length, then it becomes plate. So plate is having two dimensions appreciable as compared to the third dimension. And in general, if all three dimensions are not small, all are appreciable dimension, then it's very difficult to apply whatever the discrete theory in such system in which it is difficult to distinguish the mass and the stiffness in a discrete manner. So it is distributed throughout the system. So today we'll start the continuous system in which initially we'll be considering one-dimensional objects like beam, strings, bar, that kind of thing. At the end of this course, we will take up the plate problems also, in which plates and the what we call it some kind of membrane like the strings are there and the extension of that is membrane. So membrane also needs some kind of initial tension, then only they can vibrate. So that we'll be taking at the end of this particular course, because that is all more mathematical, because there we have two dimensional equations. So initially we'll be restricting ourselves to one-dimensional continuous system, and then so in this particular case, when the continuous system is there, let us see what are the similarity and the differences between the discrete system and the continuous system is there. So I'll share my slide so that you can so here also in the continuous system initially will be focusing on the natural modes, as we did for the case of the discrete system. So till now we consider the discrete, in which we consider the elements like mass or elasticity or the spring separately, and all these combinations of the mass and the springs we represented as n-dimensional or n degree of freedom system, and associated, then we got ordinary differential equation. So we got the ordinary differential equation with this. Ordinary differential equations are relatively easier to solve. As I mentioned, sometimes it is difficult to distinguish the elasticity and the mass in a particular element. And then we need to go for the continuous analysis, continuous approach. Basically, this discrete system is some kind of approximation to the continuous system. In the next chapter, when we'll go, we'll see that even the continuous system, we will approximate using the discrete system analysis, because the continuous system, the differential equation is partial differential equation, and if the geometry of the object is complex or the boundary condition is complex, then the solution of this continuous system governing equations are more difficult. So the only way we can able to solve using some approximate method, which basically discretizes the continuous system to n degree of freedom system. With that, we get some error in the solution. But if we take some sufficient number of degree of freedom, then we can get closer to the continuous system. And in a limit, when we take, let us say, infinite degree of freedom system, then the discrete system will approach to the continuous system analysis. So in the continuous system approach, we will be using the mechanics of deformable bodies, which is with that we'll obtain the equation of motion, and they will be partial differential equation, and depending upon the type of object we are dealing with, if it is three-dimensional object, then we'll be having x, y, z coordinate to define the position of a point on the object. And that once we are saying point can have three degree of freedom in x, y, z coordinate system. So we will define the displacement of a point in that object as u, v, w, and they will be a function of the x, y, z. So x, y, z is the coordinate of a particular point in a big object, and the whole object, if it is deforming, will be having u, v, w as deformation of that particular, or displacement of that particular point, which will vary from point to point in that object, which will be defined by the coordinate x, y, z. And here, as we had in the discrete system, we'll be having, because we are dealing with the dynamic system, we'll be having initial condition, which was there in the discrete system also, to find out the free vibration analysis. But apart from that, we'll be having here in continuous system the boundary conditions, and that's why the governing equation, which is partial differential equation, if we need to have unique solution of that, unless we have boundary conditions, we will not get the unique solution of that. And often this kind of equations are called, or this kind of problems are called boundary value problem. Just wait a minute. So as I was mentioning, this is called boundary value problem, and the u, v, w in three-dimensional object will be generalized coordinate. They will be function of the location x, y, z. So it becomes quite complex, three-dimensional. So in this particular lecture and the subsequent 2-3 lectures will be only dealing with the object which is having only displacement function of x, not y and z. Or in the plate problem, the y and z was x and y will be there, z will not be there. So the three-dimensional will be too complex to deal with in this particular course. So we will take only the two-dimensional problem only. So let us see the comparison between the discrete system and the continuous system. Some of the definitions here or the terminology which are put here, as we'll go in this particular lectures, we'll learn them. But for discrete system, you have some familiarity with the terms, like we have the discrete system, we have finite degree of freedom, like n degree of freedom we take. But continuous system, because we have infinite number of points, and each point displacement we are defining as the generalized coordinate. So there is an infinite possibility of the degree of freedom in the continuous system. So there's a main difference that the discrete system is having finite degree of freedom. We can count them, but in continuous system, it is infinite degree of freedom system. As I was mentioning, in a limit when this discrete system can have, if we increase the degree of freedom gradually, and if it becomes very large, then these two systems may become the same. Okay, so, and then the equation of motion in the discrete system is ordinary differential equation, but in the continuous system, it is partial differential equation with differentiation with respect to time as well as the spatial coordinates like x, y, z. This differential equations are relatively easier to solve. Both equations are linear, but partial differential equations are more difficult to solve, and sometimes it is very cumbersome to solve, or it is impracticable to solve in the closed form solution. Here, the eigenvalue problem in the discrete system we found in the form of algebraic equation. There is a polynomial. In the continuous system, the eigenvalue problem itself will be ordinary differential equation, or sometime in the form of integral equation. In here, the frequency equation is there in the polynomial form. Frequency equation, once we take the determinant of the eigenvalue problem, then it becomes a polynomial that is nth degree polynomial. And here the frequency equation is in the form of the transcendental equation, and the transcendental equations will contain functions like sine, cosine, or hyperbolic functions. So, and they will be having infinite roots. But in the case of discrete system, the polynomial will be having fixed number of roots. That is, if n degree of freedom, n number of roots will be there. That is related with the natural frequency of the system. So the eigenvalues are finite here, but here infinite. As I mentioned, if we increase the degree of freedom, then the discrete system can be close to the continuous system analysis. And here in the continuous system, if the dimensions are very large, like if we are analyzing a plate and the dimensions are relatively very large, then here the natural frequency will become continuous. Here, when the dimensions are not large, we have infinite number of natural frequency, but they are discrete in nature. We can able to calculate these are the natural frequency in ascending order. But here, all frequency will become the natural frequency of the system, and generally this kind of systems we analyze through the wave theory, which is not part of this particular course content. So the continuous distribution of the natural frequency will not consider in present case. Here some property like mass and its stiffness we consider as symmetric, which gives the eigenvalue real. And here we'll see that similar to the mass matrix and K matrix, here we'll be having the differential operators L and M. As I mentioned, the eigenvalue problem here is a ordinary differential equation, which will contain the spatial coordinate differentiation like x and y or z. So L and M will be some kind of differential operators which will be either x or y or z. And here, as we are mentioning the symmetry, I think here we'll be talking about self-adjointness, which is similar to the symmetry property of the matrices. So here in the discrete system, there is no boundary condition explicitly we specify, but they come inherently in the influence coefficient or the stiffness coefficient, which we calculate. But here in the continuous system, explicitly we need to satisfy the boundary conditions. And there are two broad category of boundary condition we'll encounter. One is the geometrical boundary condition, another is the natural boundary condition. We'll see those. What are those? Then the formation of eigenvalue problem is assumed in this form of equation of motion. So how we formulate this? We formulate the eigenvalue problem by substituting in the equation of motion that the time function and the amplitude part, and then we got the separation of the time dependent equations from the equation of motion to get the eigenvalue problem. Here also we'll be using this separation of variable method here because the spatial coordinate is also there. So time and the spatial coordinate solutions will assume they are separable, and then we'll obtain the eigenvalue problem for this. Here we have n eigenvalues and that many eigenvector. Here we'll be having n infinite eigenvalues and corresponding eigenfunctions will be there. So instead of eigenvector, we'll get the function here because n function will be the functional form in the x and y and z coordinate. The accuracy of the natural frequency using the discrete system, if we are analyzing a system using discrete approach or continuous approach, with discrete approach we will get less accuracy of the natural frequency as compared to the continuous system approach. Here we talked about the orthogonality of the eigenvector. Similar property in the continuous system will be there of the eigenfunctions. So eigenfunctions, whatever we will be obtaining, they will be orthogonal to each other. And then the expansion theorem we talked about here was having n terms because we express the any displacement in terms of the eigenvector. And here the expansion theorem, because we have eigenfunction infinite in number, so here the expansion theorem will contain infinite terms. So some of the definitions which maybe you're not very much familiar, like self-adjointness and eigenfunctions. These will be clear as we'll progress in this particular lecture or in the next lecture. But this gives overall how the discrete system and continuous systems are related and what is the difference and what is the association between these two systems. So now I will take up one particular formulation. This is for bending a beam. So we are talking about transverse vibration of beam. Here, let us say if we are considering a cantilever beam or simply supported beam, and then we are considering that the beam is having enough inertia as well as the elasticity, which is distributed throughout the span of the beam, and it can have distributed loading or concentrated loading we can have. So Pxt is representing that this is the force per unit length, which is function of x and time. So x is along the length of the beam. So this can vary. The distribution of the load can vary along the load. So at present we are formulating for the forced vibration, but in the present chapter mainly we'll be dealing with the free vibration. Then we'll drop this term. But in the subsequent chapters, we need to consider the forced vibration. Then this again may come in the equation of motion. So here, we are assuming that whatever the beam is there is having distributed mass and this stiffness property. Even the beam can have varying cross section. Like here, I mentioned the mass mx per unit length. So mass per unit length, which is function of x, so it may change. So geometry of the beam may change. So this is a more general formulation, and depending upon the type of solutions, we can assume this is a constant or any function of any function which the beam have. The cross section is also changing with x, so it's not necessarily a uniform beam. It can have different cross section. Like if it is a circular, along the length, if you cut the beam, it will be having different radius of the cross section. So that kind of a formulation we are talking about. Even the area moment of inertia, Ix, that is also changing with the length of the beam. In this figure, it looks uniform, but the cross section can change. And for formulation purpose, we'll take up one small element at a distance x from one end, and the element is having small width dx. Total length of the beam is L. So I think I have defined all the variables. So here you can see that now the force, the mass, area, everything is now function of x, which was not there in the previous case when we talked about the mass. Then we talked only the m1, m2, m3, but it was not function of x, the spatial coordinate. Similarly, the force, it is function of x as well as the time. So now we'll focus on this particular element. I'm taking out this element and trying to draw the free body diagram of that. So here is that small element which was there, and during deformation it took this particular orientation. Here, if you see this particular element is having y displacement. So initially the beam was here, the static equilibrium position is here. So the linear displacement of the beam, the center of this particular small element, is y. This is the translational displacement or the bending displacement, y, which is function of x and t. So this displacement will change along the length of the beam. So this is one displacement. Another is this phi x. Phi x is the tilt of this beam element because of the bending of the beam, pure bending of the beam. There is another angle which is shown here is beta, which is called shear angle. What is shear angle? Shear angle is defined here. So if you have an element like this, and if you're applying force, let us say along the vertical direction, and you're fixing this end, so it will shear like this. So it will become, it will distort like this. But only thing you need to observe that this vertical edge remain vertical, and so this is not tilting, but the upper part of this got the angle beta, and this is the shear angle. In the strength of material, you have seen this kind of concept in which if you're applying a shear force here on this edge, then this gets distorted, and this is the shear angle. So this is the shear angle, and this is the angle due to the bending moment. So in the element we have, this is the shear force in the left side, qxt is the shear force in the x side. Now because this element is having so in this particular small element we have the distributed force here, because the length of the beam is dx. So if we multiply the force per unit length with the dx, so we will get the total force on that particular element. The shear force in the other edge will also be there, and that will be different because we are having the loading. So the shear force in the left side and the right side will be different. So this is the shear force in the left side plus some change in the shear force with respect to the displacement with respect to the x, and multiplied by the width of the element. So this is the shear force in the right side. Similarly, bending moment is there in the left side. This is the bending moment, and in the right side also will be having bending moment, but it will change because we can have the inertia, the rotary inertia of this. So this is change in the moment along the x-axis and into the element length. So I would define all the forces in this element: shear force in the left side, right side, bending moment in the right side and left side, and this is the external force. And we have this is the slope due to the bending. Phi x, phi is the slope due to the bending, and beta is due to the shear. Here again, I'll repeat that because of the shear effect, this element is having slope, but this element is not tilting as is tilting with by the bending case. In bending case, the whole element is getting tilted by phi angle. So if you see, this is the phi angle. So the beam got tilted by phi angle, but not because of the beta. Beta is the shear effect which keep the vertical edge to vertical only. So the tilting is not taking place because of beta here. And so this total slope due to the bending and the shear can be represented as the transverse displacement. Transverse displacement contains the effect of the both this contains the effect of both the shear as well as the bending. So if we differentiate that, so that will get the total slope, and that is represented as summation of the bending slope and the shear force, shear angle. So I think this all variables, everything is defined in the slide. So now here, first aim will be to obtain the kinetic energy of this element and then potential energy, and then we need to apply the Hamilton principle to obtain the governing equation. So, and we have some relations which we, from the strength of material, we know the bending moment is related with the bending slope like this. So beta is the bending slope. I'm not writing y here. Generally, you write EI del square y by del x, but this is the bending moment. Corresponding slope is this. So dy by dx, which contains the shear part also, is not there because this is the bending relationship. So only the slope due to the bending is coming here. So this is familiar with the strength of material concept. Shear force is related with the shear angle, and this particular equation was given by Timoshenko. With this, in this particular case, the K prime is a numerical factor. It depends upon the geometry. Tables are there in the books. If you find the shear factor for geometry, you can get the values of this. So this shear factor is a constant number, and the shear force is expressed like this. And the advantage of this is, okay, this simplifies the analysis. If we don't take the effect of the all geometry here, only take the factor, and then we have the simpler expression. So the shear force is expressed by this, and this is due to the Timoshenko who gave this expression. Here you can see that the G is the modulus of rigidity, and A is the cross section area, is the shear. G is the shear modulus. Okay. So now, as I mentioned, we will be using the extended Hamilton principle to formulate the governing equation, which will be the boundary value problem. So let us take the kinetic energy. So kinetic energies will be having two parts. One will be the translational motion, that is up and down motion, which will be having contribution from the bending as well as shear, because we have seen in the previous slide this y is the effect of not only the bending but also the shear, because shear is making this displacement. So translational kinetic energy will contain both the bending and the shear effect, and the rotary inertia. The rotary inertia will contain only the bending, because we have seen that the shear is not making this element to rotate. Only the bending is making it to rotate. So the rotary inertia will be only due to the bending. So here you can see y contain, so this is nothing but half mass and velocity square. And y contain both the bending and shear effect, that is the translational motion. This is the nothing but half J is the polar mass moment of inertia per unit length, and this is the angular velocity due to the bending. So this is the rotary inertia, which is only function of bending slope. It's not function of shear effect. So here I will define this Euler-Bernoulli beam theory. Euler-Bernoulli beam theory, whatever the strength of material you studied, there is a pure bending case. Whatever the relations you derive, that was for pure bending case. So that beam is called Euler-Bernoulli beam. If we consider this rotary aspect, rotary inertia also in this Euler-Bernoulli beam, then that particular beam is called Rayleigh's beam. Rayleigh's beam will include not only the bending but the rotary inertia part. these are the theories in which we try to include higher order effects. So rotary inertia is something like higher order effect. So here we got the kinetic energy and the mass moment of inertia per unit length can be expressed as mass into radius of gyration square, and then radius of gyration can be expressed like this. So finally this can be written as rho into I, where I is the second moment of area per unit length of the cross section. Previous kinetic energy, if we take the variation of that, so here we have two generalized coordinates. One is y, translational displacement, and it is the phi, which is slope due to banding. The other angle, the slope due to the shear, is related with the other two, so they are related. So among these three, we are choosing the phi and the y as the generalized coordinate. Beta is related with that, so that will not be a generalized coordinate for us. So in this, if we take the variation of this kinetic energy, we will get expression like this. This kind of variations we have done earlier. So this is a mass. If we go back here, because here twice is there, so variation will be having operation similar to the differentiation, and even it can come into the integration within the integration. So if we take the variation of this will be 2, same quantity, and the variation of this. So same thing has been written here. This for the first term, and this for the second term of the kinetic energy. So we have taken the variation of this because in the Timoshenko, in the Hamilton principle, we need the variation of the kinetic energy term. So a priori, we are simplifying these expressions. Then in Hamilton principle, we have the virtual work. So virtual work are having two parts. One is due to the conservative forces, another due to the non-conservative forces. And the conservative force part, virtual work, we are related with the minus of the potential energy variation. So this can be written like that, and this will be in terms of the external force which are acting. So Pxt was the external force per unit length, and y is the displacement in the vertical direction. So variation of that will give us the virtual work due to the non-conservative part directly here. And the conservative part, for that we need to obtain the potential energy. So potential energy is obtained like this. So potential energy will be having two components. One will be due to the moment, bending moment, another due to the shear force. So for bending moment, this is the slope, change in the slope, and if you multiply the length of that, so this is the change, total change in the slope in that small element due to this moment. And if we integrate from 0 to L, we'll get the potential energy of the whole beam. Similarly, here the force and force into the displacement. So if you see in this figure, this is the element which got sheared because of this shear force, and this beta angle is the shear angle. Because width of this element is dx, so this distance is nothing but angle into the width of this element. So beta dx. So that means this during the shear, this force got displacement by this much amount. So if you multiply this shear force with this, we will get the shear force or the potential energy due to this shear force of this element. And if we integrate from 0 to L, we'll get such virtual potential energy for all the element in the beam. So this is the shear force contribution. This is the bending moment contribution. Again, here the Euler-Bernoulli beam theory does not contain the shear effect, only the bending moment effect it considers. So if we ignore this term, then our analysis will be only the Euler-Bernoulli beam. Another thing was if this particular shear effect, if we ignore, and in the kinetic energy, if we retain this rotary inertia, that is the Rayleigh beam. So Rayleigh beam contains this translational motion, rotational motion, and the bending effect. Shear effect is not there in the Rayleigh's beam. But if we consider all these four effects, which is there in the previous expression and here, that is called Timoshenko beam. So Timoshenko beam theory contains the shear effect, bending, rotary inertia, as well as the transverse displacement. All these effects are called Timoshenko beam theory, and we are deriving the more general expression of the Timoshenko beam theory, in which all effects are there. And if we want the Rayleigh's beam, then we can drop the shear effect. If we want the Euler-Bernoulli beam theory, we can even drop the rotary inertia. So formulation is more general at present, and if you want the simpler version of the beam theory, that can be obtained from the present formulation. So we have now the potential energy. We can take the variation of that. So once we take the variation of this, so here even this moment, bending moment, and the shear force expression we had earlier, like this, can be substituted. So if we substitute that, we'll get the square of this term. Similarly, if we put the shear force in the previous expression, with that, we'll get the beta square term. So here we are putting the shear force expression, the bending moment. So that gives this. Now we are taking the variation of this. Okay. So here, when we are taking the variation, this get, because we have phi, and in fact, beta contain the phi and the y, which are the our generalized coordinate. So when we take the variation, so this will get differentiated. So this and the variation of that, whatever is there inside. Then k prime, this is same, only the variation of the beta. So just like differentiation, twice beta and variation of beta. Twice will cancel with this. So we'll get this. Now, because this beta is not generalized coordinate for us, but they are related with the y and phi. So we can express the beta as dy by dx minus phi. So here I have done that. So wherever the beta is there, I'm writing d derivative of y with respect to x minus phi and this. So these two have been replaced here. So our potential energy now contain only the phi and the y. There is no beta because beta is not generalized coordinate, is related with this relationship. So we eliminated the beta from this. So now we got all the terms in this variational principle, variation of the kinetic energy and variation of the work done. So this we can be able to substitute in this equation here, get the variation of the total work done. So now we will be substituting this in this particular variation principle. So here again I have written the kinetic energy expression after taking the variation, then the total work done, conservative part, non-conservative parts. So this I am replacing with this expression which we obtained in the previous slide. Okay, so all these three expressions I am substituting now in this expression of the variational principle or the Hamilton principle, which is basically extended Hamilton principle. So now you can see the T variation of these two terms are this and this kinetic energy term, and then we have the potential energy term, this 3, 1, 2, and 3, 1, 2, and 3. Sorry, 1 and 2. Two terms are there, 1 and 2. And then the last one is this. So that is as it is. Now, just to have compact representation, P function of x and t has been removed, but it is understood that P, which is load per unit length, is function of not only x but also t, and variation of y, which is also function of x and t, that has been removed. So this is the our variational principle. We have substituted the variation of the kinetic energy and the work done, both conservative and non-conservative part. Now here, as we have, what will be the aim next to get the equation of motion? So aim will be to expand these equations such that we get the expressions which contain the variation of the y. If time derivative is there with this, we need to do the integration by part. Here also we need to do integration by part because variation of phi is there but is having derivative. So we need to do integration by part. Here also we need to do integration by part, but with respect to x. And then here, here we have variation though and the differentiation. So the first term we need to do integration by part. The second term, if we bring the variation here, there's no need to do the integration by part of the second term. This will remain as it is. Here you can see that the we have integration inside with respect to x, and outside we have integration with respect to time. So when we require the integration to be done with respect to time, we need to bring the time integration inside, because these two integration order we can able to change. So here also we need to bring the integration with time inside, but here there is no need to bring inside. Directly we can do integration by part with respect to x, and similarly here there is no need to do the integration of time with respect to there is no need to bring them inside. So because this is a very lengthy procedure, so we'll be doing part by part. So the same expression expressed as this is the I1 integral, this is I2 integral, this is I3 integral, this is I4 integral, this is I5. So one by one we'll take, I1 will take first and like that, and we'll do expansion of that, we'll simplify, and then once we are done for individual all the integral, we will substitute here, and then our aim will be to segregate all the terms containing phi y, this variation of y and variation of phi in one place, and other terms not containing double integral in other place. So that kind of manipulations will be doing it. So I'm stopping here. If you have any question till now, then you can ask. The detailed integration by parts I will do in the next class, because that will require some time, 10-15 minutes, because these steps are very important. Because once you understood the steps, the procedure, if you have been given the kinetic energy and potential energy, you can able to systematically obtain the equation of motion. So I will be going slow in explaining the steps so that you understand the steps, so that there is no rest of the things is then mechanically you can able to do the formulation. So if you have any questions on this till now, you can ask. Any questions? Because this was general theory I explained. Basically, we are developing a Euler-Bernoulli beam theory, and which is a, yeah, I think Bharat is having some question.
Sir, my doubt is not on the today's topic. I have doubt in assignment. Like I have one of the questions which has dampers, sir. How to
So,
deal with it? Like in assignment 3, we have to find the natural modes and natural frequency. So do we neglect? Can we neglect the damper coefficients? Like we can take CS0.
okay, equation of motion you can derive, you know.
Yes, sir.
Can you show?
Equation of motion is derived, sir. Like from that we have to find the natural modes and natural frequency, right? For
For
the
that you can
assignment.
ignore. For that you can ignore.
Okay, sir.
For time being, you can ignore because we are not consider the damping in the natural frequency at present, so that you can ignore. But equation of motion, I'll encourage you to obtain with damping and force, everything. You know,
Yes, sir.
as at today's formulation also, we are including all the effects, and depending upon the requirement, we'll drop some of the terms. You know. So if we want free vibration, we'll drop the force. If we want the simpler beam, Euler-Bernoulli beam, will drop the shear effect, rotary inertia. Yeah. For eigenvalue problem solution, there is no need to consider damping at present.
Okay.
So any doubt in this? Because these three theories are very important. Euler-Bernoulli beam theory is the simplest theory, which considered only the pure bending. So in pure bending, we have the translational displacement as well as the that is the main translational displacement. When we consider the rotary effect is like that small element is having not only the up and down motion, but is rotating about its center. So that's why this rotary inertia is coming, which is generally called higher order effect. And they are predominant only when the beam is thick. If for thin beam, the rotary inertia effect will be less. Similarly, the shear effect, when the beam is thick, then uh, this effect is the shearing take place. If thin beam is there, then there is no. Even I think in the strength of material book, you can find out there is certain ratio of the dimensions of the beam length and the cross section for which it should be considered as thin beam or thick beam. So there is strength of material concepts are there. So maybe you can refer to some strength of material book where they talked about the Timoshenko beam to be considered for what geometry, what should be the ratio, like L by D ratio if it is circular cross section. So that you can refer it. So if there is no other question on the today's lecture, okay, fine. So I'll stop the video.